next speaker is Matthew Yu from Perimeter Institute about infrared phases of 2D QCD.
Okay, great. Yeah, thanks everyone for the opportunity to speak today. Justin gave a very great and highbrow talk, so I'm going to go easy on everyone right now, and we're going to talk about some infrared phases of 2D QCD. This was work done with my supervisor, Joe Gomez, and Diego Del Mastro last year. So let's start off with a key problem in QFT, and also it's in line with the spirit of this collaboration, which is to study strong coupling dynamics. Now, Cyber gave a great talk yesterday about how confinement is really having to do with kind of a gapped nature of QCD in the IR. In particular, he said something about being trivially gapped. That's going to come up later on in this talk as well. So what we're going to do is we're going to consider the macroscopic limit of 2D QCD, except we're going to be a little bit more general. So I can take a general simple Lie group G, and R is going to be the representations of the fermions. And the goal is clear. We're just going to ask, are these theories gapped or gapless? So the Lagrangian is simple enough to write down. We have the kinetic terms for the gauge fields and also the fermions. And now T is the generators of the Lie algebra in some representation R. Now, a nice fact about two dimensions is that we can take the left and right sectors. So I would denote this as the fermions on the left and the right, and they're transforming in some representation of G. And something important to mention at first is there are some global symmetries. In particular, if we consider NF fermions, then we have a chiral left and right symmetry as SO, SP, or U, depending on if we're considering something that's real, pseudo-real, or complex. Okay, so basically, let me just say a couple of words about gappedness and gaplessness in general. Now, we basically have these two choices. So in the gapped choice, right, the IR is not necessarily trivial. While we have no propagating degrees of freedom, there could be multiple vacua in the IR. And usually these gap theories become kind of topological. So we could expect topological order. In the condensed matter literature, these are basically phases of phases that have kind of long range entanglement where there are non-local particles such as anions, for example, in 3 dimensions. And the gapless theories, well, we should think kind of there are some massless particles that may exist. Some of them may come from Goldstone bosons from a brachium of continuous symmetry. Some of them may also be massless, but not from a brachium of global symmetry. So kind of think anomalies here. And generally, these gapless theories become a CFT at long distances. So what we're going to do is if a theory in the IR becomes gapped, we're going to try to answer what kind of TQFT we may get. And if it's gapless, well, we can ask, okay, is there a valid CFT description that is available? And in some cases there are, and I'll present some examples. So to do this, let's start off with facts about symmetries in 2D. So as already stated by Maria, for discrete symmetries, for global, for kind of continuous symmetries, there's also Merman-Wagner, which says that basically, if we have a current for a chiral symmetry in the UV, so these are kind of the chiral symmetries that I mentioned earlier, the symmetry also exists in the IR. In 2D, any chiral symmetry is anomalous, and a theory with an anomaly yields massless particles, as I said. And so this will put constraints on the number NF and the representations that are available just by looking at symmetries and kind of 2D-ness. There's also a fact about topological orders in 2D, which is that there are no intrinsic topological orders. So we only see a count of the ground states. This is just saying that, kind of there's no non-trivial topological order that can possibly soak up any UV anomalies in 2D. And so basically a necessary and sufficient condition for a theory to be gapped is if the representations are sums of real reps of G. So much for the symmetries. Let's talk about the dynamics. So in 2D, basically what we're going to take is the G goes to infinity limit, where G now has mass units 1. And we're going to assume this to also be true quantum mechanically, that basically you can just take the gluons away. In the paper, we give some DLCQ arguments, but as Ross also mentioned in the beginning, in DLCQ, you can kind of integrate away the gauge fields. So we're going to take that as an assumption. So essentially in the IR, the effective Lagrangian is just going to be given by this kinetic term for the fermions. And so now we can apply some of the other great techniques in 2 dimensions. So starting with this guy without the gauge field, this is in SO dim R level 1 WCW theory, from which we gauge a G subgroup of SO dim R. So in the end, we have this effective Lagrangian is basically some coset description. So it's SO and over G at level IR, where IR is the Dynkin index of the representation. One thing to note is that this coset description, the symmetries and anomalies of QCD are captured by this gauge WCW. So that's one nice property that it has. So continuing on with the dynamics, the CFT described by this thing is gapped if the difference of the energy momentum tensors of the numerator and the denominator is equal to 0. Now, you can show that this holds if this Jacobi-like identity of the generators of the Lie algebra holds. And one thing that's interesting is that if it's non-zero, this thing can be shown to generate massless states, as I'll say a little bit more later on. So this is actually a necessary and sufficient condition. And this is true if this group G embeds inside here conformally. This is kind of by definition, because in conformal embeddings, basically C of the, the C's don't change, where C is the central charge. Here I'm using TSO as the canonical energy momentum tensor of the free fermions, and then TG is built out of the currents kind of via the Sugawara construction. Oh, I should say that based off of this, you can probably see why these generators have to appear in this relation. So now for the list of gap theories, essentially you can take G with R is equal to the joint representation that we've already heard earlier. These guys are all gapped for any G. We also have families of theories. So SU, SO, and SP, you can consider a single quark in the bifundamental. You can also consider just these guys with the rank 2. So think the symmetric or alternating representations. And then, of course, because I said we have conformal embeddings have these isolated theories. So as an example, you can have F4 with a 26-dimensional one, say spin 9 with a 16-dimensional one. And of course, you can take combinations of the above. If one thing's already gapped and another thing's already gapped, put them together, they're also going to be gapped. So here's the list. And essentially, this is the complete list and classification of the gap theories. So if anybody on the streets Princeton asks you for a list of gap theories, here it is. And you see essentially these are the rank 2 guys, these are the families, and these are kind of the isolated theories here. So let's run through a couple of quick examples. So I said G with an adjoint fermion is gapped. So in the IR, you just see a count of the vacua. There's 2 to the rank of the group. And the IR coset is given by this thing, where now H, the Dynkin index becomes the Coset number in the adjoint representation. You can also consider, say, this one. This one is not on the list, the 7-dimensional representation. So it's gapless. The IR coset is given by this one. And nicely enough, this gapless theory, we can actually give a CFT description. It's the fermionic tricritical icing. So this is C equals 7/10. And what's nice enough is that we could have also matched kind of the most relevant operators, namely the mass operator, and maps to the guy here that has conformal weight 1/10, 1/10. Now, to go to the fundamental ones, these are also gapless. There's an exception though. If you take G is equal to SO or SU, and NF equals to 1, the theories happen to be gapped, but the rest of them are gapless. The IR coset here is given by this thing, where nu is just a number based on whether or not I'm working kind of orthogonally, unitarily, or symplectically. So we have these descriptions. So I want to say a couple of general facts about this coset. And so, as I said, this algebraic description is via this gauge WZW. And the Chiral degrees of freedom in the quotient is given by kind of the branching functions. So take chi as the character of the numerator. Chi h is the character of the denominator, and you have these branching functions, which is essentially kind of matching the Q expansions on both sides. So if a theory is gapped, then this thing here actually does not depend on Q, and it gives us, and it's just a number, and it's just going to give you a count of the vacua. If it's gapless, then essentially each one of these things counts the states that are at L0 is equal to n. So for example, this guy over here, if it were gapless, then we said before that the difference of the energy momentum tensor could have generated gapless states. These are the guys. And so from the coset, we can also get other things such as modular data, scaling dimensions of operators, OPEs, etc. And we go into more details in the paper. So as a quick summary, let me just say that we gave a list of gap theories, and anything not on the list is gapless. In the low energy, we have a TQFT or a CFT, and sometimes we can give nice descriptions of the CFT as something else that's well known, say as a minimal model. And it's also possible to access dynamical data of the QCD theory from this RCFT perspective. So that's the end. Thank you, guys.
For a great talk, Matthias.
So I cannot quite remember, but I thought this conformal embedding condition is also related to symmetric spaces. Is this?
Yes, exactly.
So this list is basically the symmetric space.
Yes, you can also map this to basic symmetric spaces, and there's also a classification there. You don't have to use groups, but you could also consider symmetric
So this
spaces.
list was basically just what you would get from the symmetric.
Exactly. That's also true, right?
So the criterion is that the CUV minus the C that's removed by gauging is 0.
Right. And the criterion is exactly the difference of the energy momentum tensor being 0. It's necessary and sufficient.
And for non-compact cosets, does this specification also exist?
Well, we were just considering kind of compact.
Yeah, no, I understand, but I was just wondering if
Then I'm not sure. Probably not, because the classification or the representations of kind of non-compact Lie groups is much harder, right? So I couldn't give you like a full list of things.
Any more questions? Okay, let's thank